So yeah, look, if you look at some words like NISQ, noisy intermediate squall quantum error, I already said that. There is a threshold theorem, which of course, the threshold theorem, I'm not an expert. I think there are way more experts here in the field on fault tolerant. But what I learned is that this is starting from a particular noise model, where essentially you have a little bit of error in every qubit. But I claim there are other noise models, which might also be, physically motivated, which do not come from independent errors in every qubit, but from other error models. And that is a little bit the focus of this talk. And if I want to give you a message, what I want to convince you, I'm a mathematician. I like these estimates. That's my bread and butter. And the main message which I want to convey is there may be some ways to prove something for long-time behavior which has some impact on small-time behavior. So that's the message which I want to convey, and I will try to tame it into some kind of estimates or definitions, right? And by the way, some of our motivation comes from operator algebras and non-commutative probability and geometry. So I like these mathematical tools because, as we've seen before, you have these large operator algebras. Maybe there is some connection between these tools, and we want to see more of those and more precise. So noise models, we have single qubit errors, noise given by channels. I will talk about that. The continuous noise model, which often is motivated from research in photonics, comes from Lindbladians, right? I mean, they have a master equation, and then they have continuous noise given by a semi-group of channels. I will make that more precise later. And there's actually something like non-Markovian noise, which I will not discuss. I just want to say that there is more. I mean, what I'm starting to present is just the tip of the iceberg of things we actually should understand. For instance, imagine you have an active quantum computer, which I cannot really imagine, but you can look it up, and it is noisy, right? So there's some noise evolution. Now, what you have to do in order to start a new computation sometimes is to reset it. Imagine you can automatically reset it, right? Noise reset, noise reset, noise reset. That are noise models which have been studied in photonic papers. I mean, I found a paper where they somehow write down the time evolution of these objects, and I think that's pretty realistic and something which we should create a theory to understand well. And so that's something I found interesting and find kind of natural. We will probably not go there because we first have to understand the noise part of the noise reset, right? Okay, so yeah, what's the difference between a circuit and a channel? My computer broke, so this is handwritten on my iPad. A circuit, well, you start a state, you apply a unitary, you get a new state. What happens, what's the difference with a channel? First off, the unitary actually does not only act on the state, but also some environment. You throw something away to the trash, but the output is not a state, right? I mean, that's the difference between channels and state. The output is not a state, it's a density, right? I mean, it's immediately mixed, right? So we cannot write it as a... So many of these pictures, if you look at pictures of gates and circuits, they do not really fit. I mean, you can, of course, go on forever. And in fact, for what they did in this theory of semigroups, they actually created a long chain. If you iterate that, they created a long chain and then do the throwaway part at the very end. So at every part, they somehow have a new environment, which maybe is here, and then you apply a new unitary here, and then you do a new one here, and so on, right? So you can actually iterate this procedure if you wanted to have a noise model, and then you can throw away everything at the end, right? If you want to actually realize the composition of channels. That's exactly what is done. And this picture is super well known in quantum information theory by the so-called partial isometry. Okay, so this at least tells you we have to be careful. So what is a channel? A channel is a completely positive trace preserving map from one space of, so I write here L of A for the linear maps on a Hilbert space A. And as in quantum information useful, you sometimes want to name them, right? One is Alice and one is Bob, right? So that's just A by A matrices and a channel. Okay, so completely positive trace preserving. That's like, yeah, what we have to do. And there are many ways of writing this, and you maybe have seen the way of writing it with Krauss operator. So by the way, I'm in the math department. My dagger is a star, but I have another use of the dagger, right? Vj rho Vj star. You can also write it as trace of V rho V star, where you do a partial trace over the environment, essentially this sum with that trace. Or you want to have a unitary. Some people, I heard, like unitaries. So you can tensor with some dummy state, and it doesn't have to be 0, 0. Nobody forces you to, you could do anything. In fact, sometimes it's a good idea to maybe allow different ones, and then you conjugate with a unitary, and you also trace out over the environment. By the way, just if I talk about partial isometry, I mean that V star V is the identity on A, right? That's what I mean. But VV star is a projection, right? But of course, you know, because the dimensions don't match, it's not necessarily the projection onto A, right? So that's the new structure. Instead of unitaries, we have to accept these partial isometries, right? So if we want to understand a channel, I give you V, you know what it is, right? That's a strategy, right? They're indexed by these V's, like before they're indexed by these unitaries. Yeah, and yeah, if we use this 0, 0 vector, I will say that this implements my channel if we are looking at simulation problems later on. Okay. Yeah, you could actually play around and say, okay, maybe I have my noise model, which is this channel, and I want to write down a gate so that I can actually program that on a quantum computer, right? If the gate is nice, I could hope that you can really send it to IBM, write this program, and then they do it for you, right? So in order to do that, you have to maybe accept an error, right? I mean, maybe we can only implement our channel up to an error. So what is the way to measure errors? You want to take the difference of two channels and measure their error, and what is usually done is a diamond norm. So we're taking the supremum, trace absolute value of U tensor identity applied to a pure state. This psi here, by the way, is that psi. And then we calculate this value, and the largest value we call the diamond norm. So this is the norm, how we distinguish how far two channels are, whether they are close or not. Yeah? So that's a standard way to work with the diamond norm. And then you could say, well, what is an epsilon implementation? If I find a unitary, I tensor my rho with some dummy state, I apply the unitary, and then I get diamond norm less than epsilon. This is how I want to approximately simulate a channel with a unitary, because I like unitaries more. Or I want to write a quantum program which does that, and the throwing away at the end means simply I measure with something which doesn't touch E. It's very simple. So we can talk about these approximate implementation by a unitary. And if you wish, I mean, it's some kind of distance function. We talked about connection to homotopy. We can do a homotopy on channels if you wish, but that's just a distance function. Okay. So for instance, we could see if I have a class of nice unitaries, one which are given by my hardware, or my simulation hardware, I can take a class and see whether I can find one of these objects which simulates my given channel up to a small error, right? So that would be this distance. So this is a way to measure whether the channel I have is close to one I like, and I can write down with a unitary. So, but let's first talk about more examples of our channels. I think many people will have seen this one, the depolarizing channel. You keep one of the part, and the rest you just throw away and replace this by the identity. By the way, you could also write here any other density. That would also be a version of the depolarizing channel, and that can affect some parameters, like the quantum capacity if you want to. Okay, I think you have all probably seen the bit flip error and the phase flip error and the amplitude damping channel. This is given by two Krauss operators, this one and that one. And it's very nice in a way, you know, it tells you a little bit what channels can do, what unitaries cannot, right? So look what happens here. We have this parameter S, and we multiply this coefficient with square root of 1 minus S, and this with square root of 1 minus S, and this with 1 minus S. What happens if you iterate this procedure many, many times? You will find 1 minus square root of S to the power K, right? And here too. So if you iterate it many, many times, we will kill off the off-diagonal coefficients. With a unitary operation, that's never going to happen. Here it does happen. 1 minus S to the power K, you kill this even faster. So what will you prepare? You will prepare the state, the pure state 0, 0, right? Or 1, 1, right? So this is a way to clean up your system and reconfigure it into the 0, 0 position. That problem I've heard about, sometimes called state preparation, are exactly this kind of problem, right? I mean, you want to clear up your configuration so that you start with a very particular nice state which you want to calculate, right? For instance, many calculations here start with a 0, 0, 0 state. So if your system is noisy, you can first use a cleanup operation like that thingy, and you get the result, you know, get a better starting point for actual computation. Okay, good. So these are good models for noise models given by a single channel and iteration. And now I want to talk, yeah, I think I mentioned fault tolerant, and I'm not an expert, as I said before, but I just mentioned here that this is usually this kind of single qubit noise. And so in general, you can ask yourself, okay, what is noise good for and what is it not good for? Well, I mean, the bad news is that this threshold, if I understand it correctly, is still very small, right? I mean, if it were a little bit more flexible, we had a quantum computer, if I'm not mistaken. Convergence, so if you have some, so you have seen this before in the amplitude damping channel, right? If you iterate it many, many times, it converges to a density which has a 1 here in the first corner and the rest is 0, rather quickly, right? I mean, you do this k times, you're very close to that thingy. So if you do that and you want to prepare something else than the 0, 1, 0, 0, 0 densities, you're in some sense in a bad situation. You have destroyed information. And this, if you destroy information, that can in fact destroy quantum advantage. So I've seen some work by Stilk-Franke and Patrol and Pfefferman, which actually show that if you have too much noise, some of the quantum, I mean, that paper says actually if the noise acts too long, you actually move into a regime where simulation is more effective than any quantum advantage you have, right? That's a little bit of a bad message, right? So if the noise is converging very fast, you can destroy quantum advantage unless you use it, you know, you use some noise which helps you, right? But if you use it in a wrong way, you can actually lose all advantages we have. And there are some estimates related to that. Then I saw a paper by Chris Tunnell and his co-authors. He said, well, you know, honestly, we have done, you know, I'm coming more from the quantum information theory side, and there's quantum Shannon theory, you know, what's the capacity of a channel with so and so many copies. But there, we never actually thought about noise, right? So we thought that all the operations are done precisely, and then we have a code and see how many qubits we can send through the channel. And so all of these estimates, they should actually be rewritten accepting noise. And so what they did is they rewrote one theorem. You know, I mean, the proof before was long, but now it's longer. And so they did such a version, but they observed one thing which is very annoying. If the noise happens at the very end of your computation, you cannot do anything, right? So at the end, you cannot recorrect. So there's a problem, right? I mean, first of all, I mean, who wants to rewrite 200 pages of theory, adding noise? Yeah, that's a problem, but that's more a human problem. But so there are some better news. There are some noise models which are very natural. I will come to that. So atom arrays, phonons, photons, they have some noise models which are happening in nature. They're given there. In fact, the experimentalists have to avoid that noise to even start calculation. And yeah, and then we have seen that sometimes, noise can be used to prepare something in order to bring you to a situation where you can do a computation, right? So this is more the back. Yeah. Anyway, that's probably more on the positive note. Okay. So yeah, this is a picture which I've stolen from a paper. So imagine you have here a configuration of atoms, and you have electrons here. And of course, these electrons are not really standing still, right? So if you have different energy levels in this atom array, depending on the distance, sometimes they interact more and not, right? If they are too far apart, they cannot interact. They don't interact, but if the distance becomes too small, they do interact. I mean, this one here I will not touch, but it's a very well-known model from quantum optics, and so they can write down the equation which masters this behavior, and that is a long story. I mean, they all start from a Hamiltonian, like many of you do, and then they want to describe the noise, so the Hamiltonian has the system and the environment, and then it interacts with both. But if you want to write down what happens only to the system, you have to make some approximations. And this is this famous Born-Markov approximation. The first papers were very mysterious. I mean, there are many details, and it's really like, okay, I have to approximate this. I do this step and that step, a little bit like experience-guided calculation, if you're really honest. This has been done more rigorously recently, but anyway, after a long way, they end up with a very nice equation. What is the generator of the semigroup giving you? You start with a density, you calculate minus I times H rho plus Vj rho Vj star, which almost looks a little bit like a channel, but it's not, because these Vj's, they usually do not satisfy. So here we had summation Vj star Vj is 1. But in this model here, this need not be the case anymore. So this becomes something else. Yeah? So in that sense, these objects are pretty familiar. We take a commutator, we take such a completely positive map, they interact. So this is called the dissipative part, that's the noise part. These guys are called jump operators. Jump operators, you have to be a little bit careful. If you come from probability, jump operators literally mean that your probability jumps and you have discontinuous paths. That is not the case here. They are jump operators because in the quantum mechanical picture, they correspond to an energy jump of an electron. But don't forget, we are measuring statistics. So what we do is we have that model and we are measuring some very large averages over the environment. So the environment paths, which you then calculate with the path integral, they are very much continuous, like Brownian motion in the stock market. Yeah. So don't think that jump operator literally means that somebody jumps. That can be confusing. And moreover, this is the generator of a semigroup with a dagger here. Without the dagger, it would act on observables, which I like more, but I mean, here we're talking about densities. So we are looking at e to the t L dagger and want to see how that changes my field. And, often master equation would say d by dt rho t is L dagger of rho. So this is the so-called master equation, right? And we want to use that. And we have here tt dagger is e to the tl dagger. This is my channel for every t, right? So this is the situation I will be mostly concerned. Yes?
Is there some constraint on the Vj so that it will preserve trace?
No. I mean, in finite dimension, we assume that to be a finite sum, but in finite dimension, that's not, Usually it's a finite sum. Is that a constraint?
But do you want it to preserve trace?
Well, the point is this is a generator. And Mr. Lindblad deduced that if you take it as a generator, it does not have to produce trace because the generator does not have to be trace preserving. Only after exponentiation it is trace preserving. And Mr. Lindblad characterized all possible semigroups of completely positive channels. And semigroup means that TT times TS is TT plus S, right? So he showed whenever I have such a map, such a family, the generator looks like that. These are all of them for type 1 von Neumann algebras. Yeah. No, that's important. Here they are not. There, you have to think about, this H and these guys, they compete. And the trace preserving property is just given for both of them individually. Yeah? This is not the channels are these guys, e to the t L dagger. And since we take an exponential, it becomes trace preserving. But you have to show that. I'm not saying it's trivial. No? Okay. Yeah. So collective noise works with very few jump operators, but I need a little bit of notation. So for an individual V here, I denote this generator here, the Lindblad generator. This 2 here is important. And since you asked, this 2 here guarantees that after taking the exponential, it becomes trace preserving. Yeah?
I mean, you want trace of this L dagger of rho to be 0.
What we want here is trace of L dagger. Yes.
And here, because of the trace property, it's exactly canceling, right?
Right. And now you see here, if you take the trace, then you can move this over and it cancels. And that is the reason for the, yeah? So that's...
On the previous slide, why that would be for general H?
Maybe I made a mistake. That's, yeah, maybe I forgot the second term. I probably forgot the second term, you're right, yeah? So, but from now on, we will use only those. Okay, good. So a very simple operator here is if you're actually right, I forgot that second formula, but these are the right ones. So the easiest jump operator I know is just take 1, 0, 1, 0, 0, right? That's a jump model, and then this guy here, you can write it down. That would be a generator. Now, what I will saying here is I will talk about here about noise models with few jump operators. There is a whole theory about Davis generators with many jump operators. That's super interesting, but I will leave it out completely today. I mean, then I need 2 talks, right? I mean, it's super interesting, but I have to make some decisions. And today I want to focus on few jump operators. Okay, so you can also do an interesting variation of that. This here corresponds to 1 electron jumping from energy state 0 to energy 1. But that happens only if your absolute temperature is 0 Kelvin. And then if you go a little bit above that, there's also probability they jump back. And the model for that, they are given by these kind of generators, where we add the LV star, but we have to use these weights in front of them. Yeah. So what happens here is that, for instance, if you take this, then but this guy here is sent to 0. Yeah. So this will be a steady state of that time evolution. Yeah. So but that's a very natural. Yeah, that's like if beta goes to infinity, this goes to 1 and this goes to 0, and then we would prepare again such a 0, 1 state, right? Okay, so we have these kind of models for preparing a particular state. And yeah, there's an extra I mean, what we have seen in the atom arrays is actually not this one, but a sum of these AJs. One single operator, so it's a sum of local operators, but a single sum, right? So we have And then they would fix, if you take the corresponding n-dimensional version, they would fix the tensor state like this, right? So this is a collective noise model, which I just wanted.
So in a real model, how do you choose the n? You have some.
And it's the number of qubits you have. It's a 1D chain. This is kind of the noise model for x and y's, right? If you have xj, yj Pauli operators, this is the corresponding noisy version of it. Yeah, we'll see an example later. Right? Okay. Yeah, so this is.
I was thinking if you do the time array, so the jump operator is a single error.
Yeah, but they will, if you do a 1D chain, they will all jump simultaneously. They will all with a certain,
Okay. It's a different model.
That's a different model. They are not jumping independently. They all jump with a certain probability, or they all go down with a certain probability. They cannot decide individually with which probability they jump. But that is the model they used in magnetic field. You have a photon, you put a magnetic field, you put it on and off, and that happens, right? Okay, so there is actually something like a super easy noise. If your noise operator is, if your jump operator is actually self-adjoint. That's the easiest noise in the world because you can write down a formula for the exponential. You just average over a Gaussian random variable, right? To the left and to the right. So this is certainly something. Okay, if somebody gives you an exercise, simulate this. Well, you just have to, average a long time, a classical average over the Hamiltonian. This is an H here. The Hamiltonian to the left and to the right, right? So this G. Yeah, I forgot the H, by the way. The correct formula is. Right, you have to use the Hamiltonian, if not, it's trivial. But then it's so if you have access to this, if you have access to the unitary evolution e to the ith, you can write down a formula in a heartbeat. Now you might worry about using too many classical random variables, but you can do an approximation. For instance, you can replace it by just 2 copies. Here's an h, ot squared, right? So you can have a very simple noise model in this particular case, just 2. Okay, so for Hamiltonian noise, where it's given by a self-adjoint operator, you have a very simple gate. Yeah, if I have time, I'll write down the gate later on. So yeah, so this is a very simple version. And then what I learned here when I talked to the crowd, that if you can actually simulate these simple noise operators, you can simulate them all. Yeah, it's very simple. You just have to know that, and then it's done. And it might be difficult in general to find these cross operators for an arbitrary system. Then you have to solve a stochastic differential equation. If you want to do it on a nose, if you want to do it up an arrow, simple. Yeah? But these stochastic differential equations, they have also been around and used. Okay, so now I will talk about convergence behavior, because I told you I'm more interested in long-term behavior and how long-term behavior translates into short-time behavior. So I denote by this guy the ergodic limit. It's a standard operation. It converges most of the time, but you can always find some convergence. And then we define the mixing time as the first time, so that this is kind of the projection onto the steady states. Yes.
I just wanted to ask a question about the previous slide. You mentioned simulation. What do you mean simulation?
Oh, what I meant is that I have a noise model, and I want to write down a circuit on a quantum computer which approximates this up to an error.
Well, let me ask something. If we were not doing Lindbladian, but we were doing Hamiltonian evolution, then
yes.
there's a whole theory where you can do, like, for example, higher order Trotter or various other things, so you may make the error go down much more rapidly.
Trotter works the same. There's no difference whether the word of Hamiltonian and Lindbladian simulation is sort of parallel, right? I mean, they're using this similar concept by different objects.
So you may simulate F to what or T to the
Trotter works in a Banach algebra if you really read the literature, and the set of CB maps is a Banach algebra. So just to give you one hint why trotterization is the same, right? I mean, there's no difference. And so you only have to understand what happens for the cost close to zero. So then, yeah. And so that theory is very similar. I think it might be even, we will talk about this later. Okay, so in order to understand this behavior, we actually have to understand something like the mixing time. So we have this projection on steady states. We ask when does the TT approximate that in the diamond norm. We can ask when does it approximate this. Here I mean the CB order. So if I plug a matrix in here, this has to be 1 minus epsilon for positive x. This has to be less than this, less than that in the sense of the positive semi-definite order. And we actually need the CB version of that. So that is return time. Return time is stronger than mixing time, so it happens later. And you can apply the same definition if you don't like continuous model. You can just take a single channel and iterate, and you would have the same definitions. And yeah, so exercise, the mixing time for our LVN is of the order log n. It's an exercise for you. You can try to prove this, right? So mixing time is not, n is the number of qubits. Log n is not that big anymore, right? Log n is a good number. Okay, so yeah, I think we have seen all that, right? This is the steady state, this is the projection. By the way, I'm very much interested on having not one steady state, but many. Why? Because if I couple it to an innocent system, I have many steady states, right? I take one tensor, an arbitrary one, and that helped us a lot in understanding things. If you want to have a very nice model, you want to prepare a given state sigma. You can write down E sigma minus identity. That's a generator of a semigroup. It has mixing time 1 over epsilon is optimal. What is the problem? If you write down the Krauss operators for that guy, they're not very local in general, right? I mean, if they were local, you have the fastest preparation time you ever could think of. You can erase every error in a very short time. The problem is the corresponding Krauss operators here are crazy. You can write them down, but it doesn't mean they are local or somehow easy to put on a computer. Good, but they have other models which are better. Yeah, and in some sense, this is more interpretation. In some sense, for certain operations, you may think of the steady states as the protected densities which you want to keep, right? I mean, if you have some logical operations, you probably want to, with the noise model, you want to keep them alive so that you can read them out and don't change them too much. This is a way of interpreting the set of multiple steady states, right? If you have a logical sequence, that's how that would work. Yep, okay. So good noise is what we call GNS symmetric noise. So we give ourselves a steady state, a fixed point state, which has this property, phi of TTXY is phi of XTTY. So it's self-adjoint with respect to one state. For instance, if you have a thermal state which decays like e to the minus beta, you can have many semigroups which preserve a thermal state. Whereas, so unless the thermal state is a trace, then that's very restrictive. But this still gives you a large class of noises. And I think these are the only one we understand well. And then there's a funny, I need a definition. There's a funny inner product. So if your state here is given by trace dx, you can define this kind of strange inner product. It's actually not strange. It has many different meanings, self-polar forms and von Neumann algebras, right? But it's one which has some very nice positivity properties, right? If you send y to d1 half y d1 half, you preserve positivity, and that's why we like this inner product. And then you can define the spectral gap of a generator simply by assuming that if you subtract the steady value at the end, so this is kind of a mean zero element. For mean zero elements, you can estimate, it's like a Poincaré inequality, this number by the energy, which is this number, right? So that's the definition of a spectral gap for a system, which you can do in the GNS symmetric case, even slightly larger than GNS symmetric, then it has a spectral gap. And yeah, here are some some estimates. For the mixing time of L can be estimated by the inverse of the spectral gap times the number of qubits and 1 over epsilon. And the similar thing is true for the return time. So if you have a spectral gap, going to the mixing time or the return time usually just costs log n. You know? So that's reasonable. It's not good enough. For simulation, you would log n, but we don't know how to do that. Okay. So then there's a way, I want to tell you a little bit of how we get good estimates. We use some Lie algebra technique. So we start with Lie algebra. This is the Lie group. We take a bracket generating system in the Lie algebra. We apply the representation and differentiate the exponential map, and then we get new operators. Since I divided by I, this will be self-adjoint operators. So what we do is we take it geometrically. You have here's your group. You have some tangent vectors. We take the representation, build again the tangent vectors, and that are the transfer tangent vectors. And then the new noise model here, no Hamiltonian. We just use that model here for the Lindbladian. We just take exactly this funny sum with plus and 1/2, and then this gives you the noise model. And it's a transferred noise model. And it's important because, So what happens here is we discussed three things: spectral gap, mixing time estimate, return time estimate. These were the three analytic properties which I care about for today. Yeah? What I'm saying is, if the Lie group has these properties, return time, mixing time, spectral gap, then all of these objects have an estimate with the same number, right? So this gives you a uniform bound for all representations. So if you have a unitary, but unitary tensor U, it gives you the same, you have the same lower bound which you derive from the Lie algebra, and there are some very nice tools to derive return time estimates from harmonic analysis. Yeah.
You're talking about mixing time in the unitary group. What invariant metric are you thinking of?
I used here the one I'm using the the mixing time in the unitary group. That would be the TT minus E infinity L1 norm, so L1 to L1 norm.
But aren't the relevant norms there have gate dependent? The relevant norms in mixing in the unitary group should be heavily gate dependent, right? I mean, it's not equal.
Yeah, I mean, I use the corresponding groups there are classical systems. So if I want to have something like diamond norm, I do L1 to L1, right? So I TT minus identity from L1 of the group to L1 of the group.
Yeah, I'm thinking of like Brown-Susskind norms.
Can we talk about that later? Yeah? Good. Okay, so some examples here is, this is an example. So we could take this self-adjoint version with xj's and yj's. And this would be the non-self, the kind of the noisy version of that guy. For this one, we have, this is incorrect. Sorry for that. This is a mistake I do all the time. And so the first one is, so I'm using them. So this is probably good I made this mistake. So I'm actually not changing every xj. I'm taking them all simultaneously, right? And then I form the noise model with these new Krauss operators. And for that model, for beta here, we have the spectral gap for these guys is uniformly bounded, but for these guys it's not, right? So the beta actually changes the spectral gap properties. And so this is some kind of, noisy version of the xn's themselves, right? So here we have some kind of phase transition between, The point here is that these guys here also satisfies L of 1 is 0 and L dagger of 1 is 0. So the semigroup is both trace preserving and unital. And that happens for the first kind of models, but no longer for this one. And it's good to think of something like death birth process would produce such a thermal state, they also fall into the similar category. So it can happen that we have different noise models. We have relative entropy, and that is kind of a standard inequality we are looking for. We want to know that the relative entropy here decays, and then we call that constant alpha. And then what was proven is that for every GNS symmetric Lindbladian, we always have some constant, which works. And then later on, we were able to prove that if we have a return time estimate, we can also bound this constant here from below. So return time estimate implies entropy decay. And I will give you a little reason why I think that is interesting. So if you have entropy decay, you could think of having the noise being intercepted by some other channels, right? I mean, that's what I said before, noise, some intercept. Or imagine your noise works, and then you do a little error correction, and then you do noise, and you do error correction. So if these noise operators preserve the steady state, you still have entropy decay. You can use data processing inequality, and you just sum up all the time instances. So if your time is t, but you intercept as often as you wish, you will still have decay. And if you have decay, it will still converge to the steady state after some large time. So independent of the number of intercepts, even if these are very small intervals, if the sum of them is large, you will have decay properties. And in particular, you will have decay properties for the L1 non-distance, is one they often care about, right? So this means if the intermediate operators preserve your steady states, there's no way you can recorrect the errors, right? Unless they are in the steady state subspace, right? So there's some kind of, because eventually you will converge to this steady state. I mean, there's nothing you can do, right? You cannot, whatever you did in the middle doesn't help. Okay, so how much time do I have left? 7 minutes, good. So I have some application to logarithmic complexity, and I might have to skip one of them, but I will do So what we did is, we actually saw a nice paper by Jaffe, Lloyd, and 2 of the students, where they were introduced, let me write down here. Let me start from the back of the slide here, okay? So they were interested in gate complexity, but they insisted on making a convex function on channels, right? So a measure of complexity which is convex, a convex function on the set of channels. And then they wrote down what they call axioms, or desired properties. You do nothing on the identity because doing nothing should cost nothing. We could discuss that forever. You should have some additivity property, like if you combine one good gate with another good gate. We want some complete additivity property. So if you take a tensor product, that's the sum of the costs, and then some continuity bound. And this constant here is important. Now, they found such a model of complexity, and they found what is the continuity bound here, and they actually imposed that the continuity bound is the number of qubits. Yeah? So if you do that, you will never see exponentially long. Yeah, the worst thing you can see is log n, because it's part of the fourth axiom. So what we did is, okay, let's look at these axioms and see how we can actually find new models of that. They had one model, and we said, okay, we can do many models. So our model is we start with a set of resources, just an arbitrary set of resources. This could be your local gates, but maybe you have transformed your local gates into some other sets of gates, and they're no longer local, but you remember what they are. This could be either unitaries or self-adjoint operators. And then we punish channels if they take operators which commute with all of these resource sets and make them large. And that is our analytic expression, right? I mean, it's really like a...
Right, what is S prime, the commutant?
S prime is the commutant, right? So ES is this projection which we need, right? And that is kind of the worst case scenario, right? It turns out that is the worst case scenario. Okay, so I said that they showed that for this Wasserstein-1 distance, this grows with the number of qubits. And by the way, if you take this system here, that is equivalent to the Wasserstein distance. And then we proved in full generality, if I use this noise model here, so I put I take this Lindbladian, I use the jump operators as a resource, then I can always prove that I have an upper estimate on this continuity bound, which is dominated by this CLSI constant, square root the number of terms, also this is square root of m and log a. So we have two square roots here. And if you take this example here, well, there are 2m many terms, square root of, 2n many terms, right? Number of qubits is n, 2n, square root of 2n, square root of 2n, because we are in dimension 2 to the n, exactly gives this logarithmic bound. So in other words, the entropy inequalities imply that these complexity parameters grow logarithmically in the number of dimensions. Yes?
The Wasserstein distance is applied to density matrix or another sort of...
It's a quantum Wasserstein distance, which somehow is defined by using conditional expectations. Right? So we have that, and we have many more examples where we find this bound. And then we apply this. I want to give you some examples how this applies. So if, for instance, a unitary is here, then the complexity of this gate at u rho u star, is less than 1, but it's very simple. And if you have s's and s, if you do a time evolution, e to the its, it grows linearly. So what this means is that if we have a semigroup and ES is this projection onto the final state, then we can actually prove if we have a return time that eventually we will reach almost the maximum. We maybe don't exactly reach the worst bounds, but up to an epsilon. So this is like in Brown-Susskind, right? If you wait long enough, the semigroup will achieve the worst case, right? So that is a parallel to, one of the parallels to Brown-Susskind. But it gives you an analytic way to somehow find lower bounds, which are usually hard, right? I mean, so long-term estimates give you lower bounds for these things by just looking at these guys. And in full generality, in finite dimension, at the beginning you have always linear growth, right? So it grows linearly and then saturates, exactly what you expect from Brown-Susskind, but somehow polynomial in time. Not exponential. That's because they are normalized to the logarithm, right? I mean, that is kind of built in, so you cannot reach exponential. It just gives you some good behavior at 0, and it reaches some saturation. And for Hamiltonian simulation, we did an example where we take a Hamiltonian, literally Hamiltonian, probability, norm less than 1. We use the building blocks of the Hamiltonian as our resource, because that's what we have, right? If you don't know what locality means, you take the building blocks as your resource. Then we found a very nice result by Campbell. This is the famous Q-drift. It gives you a very good approximation. Then you can approximate this unitary evolution by a channel, also by a very nice approximation. Then you apply this to the complexity, and we find if we take the resource complexity adapted to the building blocks of the Hamiltonian, it grows linearly in T with different constants, right? Because at the 0, it's hard to make that precise. And then we can actually prove that unfortunately, with rather low probability, even the simulating gates, right? So the definition of this Q-diff procedure is you take long averages of the individual gates to the power tau, right? So e to the power h1. So what we can prove is that with low probability, we actually exhibit some linear growth of complexity. And linear growth of complexity is a lower bound to some circuit complexity. Yeah? So we see some kind of Brown-Susskind behavior. For small values, it's a little bit shaky, but it gets very steady You see some linear behavior. And the funny thing is that we even find that if we don't do anything. Right? Okay, so imagine you have a Hamiltonian. Imagine you have a Hamiltonian where here hj plus 1 is minus hj. Nobody prevents you to take minus hj in the next step, right, with the same probability. So, but you don't know, right? I mean, they're unknown. So it could happen that your h is 0. So you're trying to simulate the world when it stands still. But your model to do that is to use these local Hamiltonians. And you're looking for a random gate which does that, some e to the I tau. So you have to use them. And what we prove is, even if the world stands still, because you chose a certain model, you will still pay a price. So imagine that, right? I mean, actually it's like math, right? You want to prove something, you work all day, nothing has been proven because you're trying to do nothing. But the work of simulating it costs. You literally are tired at the end of the day. Okay? That is the model for that, and that is our motivation to prove these lower bounds. But in order to prove them, we have to use this whole Lindbladian machinery. Right?
May I ask a question on a little bit? So you are considering the Hamiltonian simulation with the presence of noise. So you are trying to simulate it.
No, the noise has gone. I'm using this set, as a resource, right? Because, I mean, in some sense, this is what we are given, right? What I'm using is I'm using noise estimates to show that even if I try to do nothing, I will say a price. So I'm using noise just as an intermediate tool to prove the lower bounds. But then here I'm simulating the Hamiltonian on the nose. By the way, by a channel, right? Which I find amazing, right? I mean, you simulate a pure unitary evolution by a channel, but that's what Mr. Campbell did, and it's a great idea, it works, right? But if you then try to simulate that with your elementary e to the t h j gates and you write long products, they will still be expensive, even if your Hamiltonian was trivial. Yeah? I have another application, which I will just tell you the definition, okay? It's 1 minute. So what I did here is the following thing. I have a given channel, phi, and I could ask what is the simulation cost, so the smallest steps of a family of unitaries which simulates this channel. Yeah? And then if I define that, I can also define for a given. Now I'm back in a noise model. I have a certain noise model. And I ask, what does the simulation cost with approximate cost t to the alpha when t goes to 0? Because as you mentioned, trotterization works. If you know what happens at 0, you can extrapolate and get it for every larger time. So if you do that, you can ask, is there a gap, right? I mean, what happens for this limit to 0? And what we can prove is we can prove a lower bound on that gap using the return time. Yeah? So we have this approximation, and then what we can prove, and that's something we discovered here, that we find a lower bound on the gap using this complexity constant, which we defined with the help of the operators. And if we take this operator here, this guy, then we can actually show that the gap really is like the number of qubits. So this is another phenomena where we can use this long time return time estimates to show that if the number of qubit grows, this gap also has to grow, right? And that essentially means that if you fix some order of approximation, you should always expect for noise models the number of qubits times the polynomial. Right, so you should be able to approximate it the number of qubits times polynomial time for large T. Yeah? And that's what we expect to happen, and this is just one example where we can actually literally check that that works, right? But the funny thing is that we can also prove that if the number of qubits grows, this gap, right, the smallest gap at 0, actually is not 1 or 2, it grows with the number of qubits, right? So it's really a system invariance, right? I mean, you can still feel the number of, I mean, you all know that we can still the field, but that's an analytic estimate, which tells you this gap grows like number of qubits. And that's a very optimistic case. Of course, we would expect that for all noises to happen, but, far away from proving upper bounds, right? Yeah. That if you can do time times qubits, I think that's what everybody expects to work eventually, right? Good. Thanks for listening, even with my 1 minute overtime. Yeah, and I really want to thank IPAM and the organization and you for listening.